So we're going to go through the derivation of the equation that describes the electric field on the axis of a charged ring. As part of this, I'm going to ask you a few conceptual questions. We're going to have a charged ring, and the coordinate system will be oriented such that the z-axis points straight up. And then, let's see, x, y, and z. So when I say the electric field on the axis of the charged ring, we're going to be talking about the electric field on this z-axis. First, though, these questions will help us think through the process of setting up the integral. So what do you think about here? Okay, the correct answer here is C. As a reminder, we're adding up all of the little point charges and their contributions to the electric field at the point of interest. dE is this magnitude right here that represents how strong the electric field would be due to that one piece of charge. So they're calling that piece of charge dq, just using a capital Q instead of lowercase q. That's fine. R squared is what we would need in the denominator. This is what we mean by lowercase r. It is always the distance from the piece of charge we're talking about at the moment and the point where we're trying to find the electric field. So, Pythagorean theorem, this side is h, meaning how high above the ring along the axis we're talking about. And this they've labeled as capital R, meaning the radius of the actual ring itself. So once we have R is the square root of h squared plus capital R squared, we have to square it, and that's why we get C as the correct answer. So this is the first step. I have another question to go along with it. Here is our next question. What do you think about this one? The correct answer is B. The z component right here. This angle would also be right here, and that makes this z component of the electric field adjacent to the angle. DE is the hypotenuse, and so cosine of that angle would be EDE, the z component specifically, over the magnitude. And that's where this z component ends up being dE cosine theta. So this is going to be accounting for the r hat piece of our integral to account for direction. Now, I do want you to think about why we're not being asked for x and y components. Each electric field is going to have x and y components as well, but if I think about the dq, that's exactly opposite this one, its x and y components are going to cancel. So the x and y components of the electric field are going to cancel out. All of the pieces of charge, though, if we think of all these pieces everywhere around the ring, all of them are going to be creating upward electric fields. And so that's why we're only caring about the z component. That's all we're left with after we integrate. So I have one more question for you, and then we will set up our integral. Okay, here is our third question. Correct answer is D. So cosine is adjacent over hypotenuse, which is the r. So the lowercase r specifically. So h over r. But remember, we just said that r is the square root of h squared plus this capital R squared, where capital R specifically represents the radius of the ring itself. Lowercase r is the distance between this charge and this point where we're trying to find the electric field. Okay, these three questions, the reason we're asked is because we're going to put them together. They make up the pieces that we need to substitute in to our equation to integrate to find overall electric field. Okay, so we were asked for dE first, and then the z component. So dE was dq. They had the 1 over 4 pi epsilon naught dq over r squared ends up being this h squared plus r squared. So that's the dE, meaning the electric field, the magnitude of it due to that one piece of charge. But as we talked about, it's only the z component that matters. Those are the ones that are going to add together. And we just found out that is dE times cosine theta, where cosine theta is h over the square root of h squared plus r squared. So let's put some of these together and see what to do with it. Now we haven't put in like a dz or a dx. We've left this as dq. The reason why, if I come back to the picture, if I think about some other dq, like right here, the distance to the point of interest is the same as this one. These r's are the same. These are going to make the same angle, theta, with the vertical. If I look at a piece over here, this distance r is still going to be the square root of h squared plus this capital R squared. The angle it makes with the vertical, the z-axis, is still theta. So h is not changing. Capital R is not changing as we continue our way around the ring, accounting for all of the pieces of charge. So when we come down to our figure, or our equation, I should say, we've been integrating, just treating our point charges, adding up all of their contributions to the electric field. Well, this represents how each piece of charge contributes to the overall electric field. So if I'm going to integrate to find the total electric field, 1 over 4 pi epsilon naught, that's the k. That's this k in here. That's a constant. H is a constant. The h squared plus r squared, those are both constants, so I can pull out that whole quantity. And I'm actually only left with the integral of dq. And this is going to give me the electric field in that z direction, specifically along that z-axis. Well, if we integrate dq, that just means as we go around the ring, how much charge have we accounted for by the time we get back to where we started? So essentially, we're starting not encompassing any charge. By the time we get back to where we started, we encompass the total charge the ring has. And so this ends up representing just the overall total charge on the ring. So this equation, E sub z for this ring, this is what it looks like. This is specific, though, to a ring where the z-axis is specifically going through the exact center of the ring. And then this equation in h is however far from the center of the ring to this point of interest on the ring. That will give us the total electric field at that point. In your test notes, they have this equation written this way. And hopefully it will make sense. So instead of h, they're using just the z. If the origin is the center of the ring, then what z value? How far from the origin are we talking about? This equation only works as long as the z-axis is going through the absolute middle of this ring. But the nice thing is, since this equation's in the test notes, we can totally use it. You don't need to derive it again. We went through the derivation to practice the thought process of setting up the integrals. But this particular solution is in the test notes. It's not going to be the case for all the lines of charge. But for the ring, it's right here.